Okay, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good night, everyone. Okay, so in this session, I would like to briefly introduce moment distribution method, chapter number 12 in the textbook, Hibler textbook, chapter number 12. Okay, moment distribution method. So moment distribution method is actually called as displacement method. It's called as displacement method. So we will review the textbook tonight, displacement method of analysis, and it is easy to apply. Okay, in this chapter, we will first state the important definition and concept for moment distribution, and then apply the method to solve problem involving statically indeterminate beam as well as frame. So we do not calculate moment in thrust. So the moment we will calculate only in beam and frame. So there are two type of structure that we will together learn. Number one is beam analysis. Number two is frame analysis. So this week, so we will focus on beam analysis. Okay. The general principles and definition. So this method, analyzing beam and frame using moment distribution method. Okay, the important in this chapter is moment distribution is a method of successive approximation. Okay, that may be carried out to any desired degree of accuracy. Okay, the process in the table, okay, is including unlocking and locking each joint in succession. Unlocking and locking. So when we apply fixed end moment, we assume that both end are fixed, and then we distribute the moment, and then we have to distribute moment, and after that we have to carry over the value. So actually the process behind that is unlocking and locking each joint in succession. Okay, the internal moment is the aim, the objective. The internal moment is objective. So when we want to analyze beam or frame using moment distribution method, so we are going to determine internal moment. Internal moment, or it can also be we can also call it as member and moment, internal moment, or member and moment, or bending moment. Okay, and we calculate the internal moment at joint, and we have to distribute moment. And after that we have to balance the moment. So there are two main process in the table. Number one is the distribution, the moment distribution. We distribute moment. Okay, we distribute the moment by times the moment at joint times with distribution factor, and after that we have to balance the moment. So balancing we will do by times the moment value with the carryover factor until the joint have rotated to their final or nearly final position. Final position means the moment in the table later on, okay, will reaches zero value, and after that the process in the table may stop. Okay. So under the moment distribution method, the process of calculation is both repetitive. Repetitive means there are two main steps in the table: distribute moment, balance moment. Distribute, balance. So we have to repeat the process until the moment reaches zero. Okay, this method is easy to apply. Okay, easy to apply, and actually it will be used to worldwide. It is used worldwide to calculate or to analyze beam and frame. Okay, so let's look at the terms, the important terms that you need to understand before we can start analyzing the beam and the frame. Okay, number one is sign convention. Sign convention. So under moment distribution method, we have to set the sign convention in our mind. So bear in your mind. So the sign convention for the moment distribution method is clockwise, clockwise, positive, clockwise, positive. The sign convention. The sign convention is clockwise positive, whereas counterclockwise negative. So this is the clockwise moment that act on member. Clockwise moment that act on member. Clockwise moment that act on member is going to be like this. For example, if we have this beam, okay, this is beam A, B, C, D. Beam A, B, C, D. So clockwise moment that act on member is this 1, 2, 3 element. Clockwise moment. Okay. This is the meaning of the statement. The clockwise moment that act on the member. So this is the first assumption that we have to follow. The first assumption that we have to follow. Okay. Clockwise moment that act on member is clockwise positive. Clockwise positive. Okay. Okay, now move to fixed end moment. Fixed end moment. So we will distribute moment in the table. So we have to have the first moment value in the table. And the first moment value in the table, we will get from what we call as fixed end moment. Fixed end moment. Fixed end moment. And fixed end moment is behavior. It's actually behavior. Fixed end moment is behavior. Okay, so what is fixed end moment? So we have actually the formula given in the final page of the textbook, which give us the fixed end moment formula. This is fixed end moment. Fixed end moment. So fixed end moment means the beam, one beam, A and B. So both end are fixed. Both end are fixed, and the beam is subjected to loading on top of the member or along the member. Okay, this P. Okay, we do not count as fixed end moment if it is subjected at joint. Cannot. If it is subjected at joint, we don't consider this. If P is subjected at A, we don't consider this as fixed end moment. Fixed end moment, we only consider loading on top of member, whether it is at the center of the beam or at anywhere on the beam. Okay, so or along the beam, or this type, the triangular load. So normally you have to remember, okay, four types of fixed end moment. This is number one. The first type of fixed end moment, the beam is subjected to point load at the center. So when P is subjected at the center, when P is subjected at the center of the beam will deflect. The beam will deflect, and there will be reaction at both A and B to counter back the bend beam to its original position. And always remember, for the beam, the original position is horizontal. Beam, the original position is horizontal. So when we apply force on top of the beam will bend. So the reaction will exist at support A and support B to counter back the to counter back the bend beam. So that is why the fixed end moment is actually behavior. Okay, fixed end moment is behavior. So we get this direction and this direction because it will push the bend beam to horizontal position or straight position. Okay, so that is why we can also find the same pattern, the same pattern of the fixed end moment for second type of beam. Okay, P not at the center anywhere. The P can be here, can be here, can be here, can be here, anywhere. Okay, and A will always be in this side, B is always be in this side. Okay, so this is type number 2. P is subjected not at the center. So still due to P that is subjected on top of the member, the beam will bend. Okay, and due to this bend beam, so there will be reaction, fixed end moment. Okay, the fixed end moment at both A and B will push the beam back to its original position. Okay, so this is type number 2. Okay, so next is this one. Okay, this is type number 3 where the beam is subjected to UDL along the beam. So again the beam will bend, so the moment is acting in this two direction. It is opposite direction. It is opposite direction so that it can push the bend beam to its original position. This is number 3 and this is number 4. Okay, normally in the question you will be given either one of these lah or combination. Okay. Okay, this is due to support. This is due to all these four types is due to external loading. Number 1, number 2, number 3, number 4. Okay, that these four type, the fixed end moment, okay, is based on external loading. P and W is external loading. However, there is one formula number 5, that you need to understand. Formula number 5, this is formula number 5. Formula number 5. Formula number 5 also, this is also fixed end moment, but there is no loading subjected on it. But this has delta. This has delta. This has delta. So due to delta at one position, so let's say we have AB like this, fixed at both end. So we have A and B, and let's say B is settled. B is settled means there is a delta. B is settled, move B from this position, move to new position, and this is delta. Okay, same like this, delta. Okay, and due to this we will get one triangular if we join this. Okay, so this is delta, so this is the triangular which has perpendicular like this, and then this is the L. Okay, and due to delta there are fixed end moment which also exist at A and B, at both position, at both support, at both support. Okay, and always remember that fixed end moment is behavior, and the moment will always push the beam, push the new beam to the original beam, to original position. Okay, original position of this beam is horizontal. This is original. And after due to delta, so delta ni we apply whenever we have support settlement effect, or we have a frame with side sway. Okay, due to this, due to delta, so the beam after settlement occur will move to this position. Okay, from original, so this is original, okay, this is new position, okay, new position which is inclined position. Okay, so we have to apply moment at A and B to push this and this point to its original position. So in order to get back to this, okay, in order to get back to original position, we have to apply moment in this direction and in this direction, so that the beam will move back to horizontal. Okay, so we have to push, we have to push back to its original position. Okay, so this is whenever B is settled. This is whenever B is settled. Because of because it is behavior. So let's say beam A is settled. When A is settled, it is going to be like this. A is settled. So this is A, this is B. This one is delta. This one is delta. So this is A prime. A after settlement. After settlement, A prime. Okay. So the new position is now this one. Original is straight position. So we have to push the beam to its original position by applying moment, like this. Okay, so this is the behavior of the beam due to delta. And we will apply the same to frame as well. Frame has vertical element, vertical member. Frame has vertical member. So let's say frame like this. Okay, side sway, move to the right direction. So this column move. So this will be delta. This is for frame. So frame means vertical. Frame, we have to consider the column. The column. So means that this is original. This is new position. Original is vertical. New position is inclined. So we have to apply moment to push back this point and this point, so that it will go back to straight or vertical position. That is fixed end moment due to delta. Okay, so in short, okay, so this is the formula. 6EI delta over L squared for the formula, and both have same sign. Okay, both have same sign. Okay, for the previous one, fixed end moment, for A and B have opposite sign. But for fixed end moment due to delta, both FEM have same sign. Okay. Okay, we move back to chapter 12 just now. Okay, fixed end moment. Okay, so due to loading, one will be negative, one will be positive if subjected to loading. one negative, one positive, opposite. If we apply fixed end moment due to support settlement, both have same sign. Okay, we move to next one, member stiffness factor. Member stiffness factor, the symbol is K. The symbol is K. So we have to consider, so this the diagram. Okay, this is the diagram. Anyway, doesn't matter. We focus on the formula because this formula we will use uh, to calculate stiffness factor, and after that the stiffness factor will be used to determine distribution factor. Okay, so one thing that everyone have to understand is when we use this formula, this is for far and fixed. Far and fixed. For far and fixed, we use 4 EI over L. For far and fixed, we use 4 EI over L. 4 EI over L. This one. 4 EI over L for far and fixed. What does it mean, far and fixed? Far and fixed refers to, okay, if we have this beam, okay, A, B, C, D. We have to be able to calculate the stiffness factor for each element. For each element. So K for AB, K for BC, K for CD. Okay. Just like we do it previously, K1, K2, K3. K1, K2, K3. Okay, K is for element. So we have to determine K for each element using the formula given just now. And we have two formula. We have two formula. One is for EI divided by L, and another one is K equal to 3 EI over L. One is 4 EI over L, another one is 3 EI over L. So when to use 4, when to use 3? Depending on far end condition. Depending on far end condition. Okay, for far end fix, we use 4 EI over L. For far end pin or roller, we use 3 EI over L. So this is far and roller or pin. We use 3 EI over L. Okay, looking at the formula to calculate stiffness, okay, there are the modulus of elasticity E. I is moment of inertia, which is depending on the cross-sectional area, and the L, length of element, length of members. Okay, means that the K value, the factor that can influence the stiffness are three: E, I, and L. Okay, so that is stiffness factor. Stiffness factor. Okay, so move to next. Okay, because after this we will determine distribution factor, and in distribution factor we use K value. It is K divided by total K. K is member stiffness. Total K is joint stiffness. Total K is joint stiffness. Total K is joint stiffness. K is member stiffness. Total K is joint stiffness. Okay, so we have to consider this one. So joint stiffness refers to A ni. Refers to A. Okay, refers to A. Means that if KAD is 1,000, KAB is 4,000, KAC is 5,000, KAD, KAB, and KAC is is member stiffness. So this is member stiffness. Member stiffness. KAB, KAC as well, member stiffness. So joint stiffness refers to A. Means that for the joint stiffness, we have Ka, which is Kab plus plus K Kab plus Kac plus Kad. This is joint stiffness. Joint stiffness. Okay. So next we move to distribution factor. Distribution factor. So what is distribution factor? Okay, if a moment M is applied to a fixed connected joint, the connecting members will each supply a portion of the resisting moment necessary to satisfy equilibrium at joint. That fraction of the total resisting moment supplied by the member is called as distribution factor. Okay, we will use distribution factor whenever we want to distribute joint moment. We use distribution factor whenever we distribute joint moment. Okay, to obtain its value, imagine the joint is fixed connected to n member. Okay, this is just how we get the formula. So focus on the final formula for distribution factor. This is the formula. df is K divided by total K. df is K divided by total K. And again, K is member stiffness. This is member stiffness. And total K is joint stiffness. Okay, member stiffness and joint stiffness. df, distribution factor, is K divided by total K. Okay, looking at the same diagram, the continuation to the previous diagram. Okay, this diagram. Okay, this is the stiffness factor given in the question, but for normal analysis, we have to determine from the formula. Okay, this is just the concept, so that is why the value is given for each element. So element AB is 4,000, element AC is 5,000, element AD is 1,000. Okay, that is member stiffness. Okay, for the joint stiffness, we have to total all. We get 10,000. Okay, so what happened next is there is an applied moment subjected at joint A. So this 2,000 is a joint moment. This is joint moment. This is joint moment which is subjected at A. Okay, this is joint moment which is subjected at A. Okay, acting counterclockwise. Okay, now we want to distribute this moment, okay, to AB, AD, and AC. 2,000 is joint moment. We want to distribute joint moment to member and moment. We want to distribute joint moment to what we call as member and moment. So what should we do? From joint moment to member and moment, what should we do? Okay, we have to distribute moment using the distribution factor. Using distribution factor, we will distribute this joint moment. Okay, we want to change from joint moment to member and moment. Joint moment 2,000, and using distribution factor, we will distribute from joint moment to member and moment. Means we will get the moment, MAB, MAC, MAD. MAB, MAC, MAD. The member and moment. Okay. So the process is, Okay, number one, we have to determine distribution factor. Distribution factor, as I mentioned earlier, okay, we get from K divided by total K. So for AB, it is 4,000 divided by total 10,000, we get 0.4. Okay, and then for AC, it is 5,000 divided by 10,000, it is 0.5. And DF is AD is equal to 0.1. And adjoint DF, the total DF is equivalent to 1. So when we total 0.4, 0.5, 0.1, the factor, the distribution factor is equivalent to 1. Is equivalent to 1. Okay? So now we want to distribute moment to AB, AC, and AD. Okay? Means that for AB, we have to times the 2000 and 0.4. 2000 and 0.4. So we will get the moment at the moment MAB. MAB. Okay, to calculate MAC, it is 2000 times 0.5. Okay, the joint moment times the distribution factor, it is 1000. Okay, and for MAD, joint moment times 0.1, it is 200. Okay, and total this, we will get back 2000. 2000, but acting in opposite. Okay, in opposite. So that at A, this is A, at A, MA is actually equivalent to 0. Okay, so this is for checking. So we have to total back, and we total back from joint moment and member end moment, we will get 0. Okay, so that is the basic thing under the moment distribution method that we have to understand first. Okay, and after that, you have to understand about what we call as carryover factor. Carryover factor. Carryover factor. Okay, for the carryover factor, we do not calculate. Distribution factor, we calculate the value. But for the carryover factor, we do not calculate the value, but we use the value in order to balance the moment. Okay, previously the two main step in the table is the distribution and balancing. Distribution and balancing. Okay, so under balancing step, we have to use the carryover factor. We have to use the carryover factor. So there are two value of carryover factor, which is depending on the far end condition. Far end condition. Okay. The carryover factor represent the fraction of M that is carried over from the pin to the wall. Hence, it is in the case of beam with far end fixed. Far end fixed, the carryover factor is 0.5 or half. Okay, so please remember there are two value of carryover factor. Carryover factor is 0.5 and carryover factor is 0. There are two value. There are two value for the carryover factor. One is for far and fixed or internal support. Okay, and 0 will be used for far and roller or pin. Okay, there are two value. Carryover factor is equivalent to 0.5 for far and fixed, And for internal support, because internal we have to always assume it as fixed end. It is internal support, all assume as fixed. So all internal moment when we do balancing, we have to times with 0.5. Okay, far end, either it is roller or pin, so we have to use the factor 0. Okay, far end, roller and pin is like this. Okay, let's say we have B, C, D, A, B, C, D. AB, far end is A. AB, far end is A. B is internal. So we only mention the end, AB. Okay, CD, C is internal. C is internal. Internal is fixed. Same goes to AB. B is internal. Internal is fixed. Okay, so BC, we will use 0.5 for the carryover factor. Okay, however, for CD, D is roller. D is roller. C is internal, D is roller. So for C we use 0.5, but for D we have to use 0. 0. Okay, another one. Let's say we have pin, roller, roller, roller. Okay, pin, roller, roller, roller. This is A, B, C, and D. A, B, C, and D. Okay, so in this case, for AB, A is far and pin. The factor is 0. Okay, BC, both are internal. We assume as fixed, so it is 0.5 for both B and C. Okay, for CD, C is internal, D is roller. Okay, so in this case, we use 0 factor for CD and 0 factor for AB. Okay, that's what it means, the carryover factor. We do not calculate the carryover, but we use the factor in order to do balancing in the table. Okay, I want to move to example in the textbook. Okay, we look at the procedure first. Okay, procedure for analysis. Okay, okay, before we start doing the distribution moment and the balancing in the table, we should calculate first distribution factor and fixed end moment. Okay, that is the first two steps. Okay, to calculate distribution factor, of course we have to have K, we have to have member stiffness, we have to know the total stiffness in order to calculate distribution factor. Okay, this distribution factor will be used to distribute moment by times the joint moment to the factor, the DF. Okay, and the fixed end moment, is the first moment in the table. The fixed end moment is the first member end moment. Fixed end moment is not joint moment. Fixed end moment is member end moment. Fixed end moment is the first member end moment in the table. The first member end moment in the table. Okay, the joint on the beam should be identified and the stiffness factor for each span at the joint should be calculated. Okay, using this value, the distribution factor can be determined using this formula, K divided by total K. Okay, remember, distribution factor is equivalent to 0 for n fixed. for n fixed distribution factor is 0, and other than that it is equivalent to 1. Pin and roller distribution factor is 1. Okay, we stop for a while, about 5 minutes. Azan, eh? Okay, so we continue. Okay, for the fixed end moment, we have to calculate fixed end moment for each loaded span. Okay, using the table given inside back cover, positive FEM at clockwise and negative FEM at counterclockwise. Okay, due to loading, because due to loading, it behave in this direction. So one will be negative, one will be positive. So for the fixed end moment, this one is going to be negative, this one is going to be positive because the sign convention is positive. The sign convention for this topic is positive. The sign convention is positive, so counterclockwise moment, the fixed end moment, counterclockwise fixed end moment is negative. Okay, because it is opposite sign. Okay, for the moment distribution method, for the moment distribution process, so assume that all join at which the moment in the connecting span must be determined are initially locked. Then determine the moment that is needed to put each joint in equilibrium. Okay, so when under distribution process, okay, we have to distribute moment. Distribute moment by finding the joint moment from the member end moment. And remember, the fixed end moment is the first member end moment in the table. Okay, the first member end moment in the table. So we need to find the total moment or the joint moment, and we distribute moment to to the member. Okay, and we have to include the distribution factor in the process. Okay, release or unlock the joint and distribute the counterbalancing moment into the connecting span at each joint. Carry this moment in each span over to its other end by multiplying each moment by the carryover factor. Okay, this is 1 over 2, 0.5, because it is far end fixed. Okay, so this describe the beam with far end fixed. Okay, and after that, we have to repeat the process. Repeating this cycle by locking and unlocking the joint, it will be found that the moment corrections will diminish since the beam tend to achieve its final deflected shape. Okay, when a small enough value, okay, small enough value means whenever the moment value in the table reaches zero. Okay, reaches zero, 0.0 something. Okay, the process of cycling should be stopped with no carryover of the last moment. Each column of FEM distributed moment and carryover moment means we have to total all the moments starts with fixed end moment, and after that the moment that we distribute and the moment that we carry over, so means that all moment in the table start from FEM. We have to total, okay, and from the total moment we get the end moment or internal moment. If this is done correctly, moment equilibrium at joint will be achieved. Moment equilibrium at joint will be achieved ni means this. Okay, this is for beam A, A, B, C, D have loading, something like this. Okay, so after settle the process, okay, in the table, so we have to total the moment. So we will have table, okay, we will have member, three members. We have AB, member AB has 2N. Member AB has 2N. So we have to count two, AB and BA. And then we have member BC. This is BC, this is CB. Member BC has 2N. NB and NC, member BC. So we have BC and CB. And member CD has 2N. So C and D. So we have CD and DC. Okay. So in the table, okay, we have DF that we calculated using stiffness factor. Okay, and then we have fixed end moment as the first member and moment in the table. As the first member and moment in the table. Okay, and then we have to distribute moment. So distribute moment. After that, we have to balance. Okay, balance, carry over, balance. You can put balance, you can put carry over. Doesn't matter. Both can be used. If you want to put balance, also okay. If you want to put carry over here, also okay. Okay, distribution, carry over. And then we repeat again. Okay, so under distribution step, ni, this one. Okay, another one is carry over step. Okay, we will distribute joint moment. Here we will distribute. So always remember, at level distribution, at row distribution in the table, we will distribute joint moment. Distribute joint moment. Distribute joint moment. And at level carryover balancing, okay, we have to, okay, at level carryover, we have to balance the moment, do balancing. Okay, distribute joint moment, we have to distribute. Okay, we have to distribute joint moment and we have to do balancing. Distribute joint moment and do balancing. Okay, we distribute joint moment using the previous value, using the upper value in the table. Okay, means that here is member and moment. Okay, this one also member and moment. The first member and moment in the table is come from fixed and moment. Fixed and moment. Okay, so we will repeat the process. Repeat distribution. Repeat carry over. Repeat distribution. Repeat carry over. Okay, until the last distribution. Okay, the last one must be distribution. We have to stop at distribution. Do not stop at carry over. Stop at distribution. And after that, we have to find the total. Start from the first moment in the table. Okay, find the total. So there are 6 value. Here, 2 value, 2 value, 2 value. So for three members, we have 6 and so it will produce 6 member and moment. Internal moment. That is the process. Okay. Okay, this is the first example given in the textbook, example 12.1. 12.1, the question is determine internal moment. As I mentioned, internal moment, we can use member and moment. Also, we can use the bending moment. Also, we can use internal moment. At each At its support of the beam shown in the figure, EI is constant. EI is constant. Okay, firstly, we have to understand what internal moment is representing. Okay, how many internal moment? So we have to back to the concept where we should be able to draw the free body diagram, of this. Okay, we separate between joint and member, okay. So this is the beam, this is the beam. Okay, okay, this is the beam. Okay, this is a continuous beam. There are three elements or three members: member AB, member BC, and member CD. Okay, there is no load on AB, on member AB. Member BC is loaded by a uniformly distributed load of 20 kilonewton per meter, and there is a point load at the center of member CD. Okay, A is fixed, far and A is fixed. D is also fixed, far and D is fixed. Okay, the distance for each members as given. So we have to calculate internal moment. So what is internal moment? So internal moment, so from this we have to be able to draw the member and the joint separately. Okay, so we have three members. One, two, three. Okay, so we have member AB, member AB. This is A and B. We have member BC, and we have member CD. And member and moment refers to this. One member has two end. One member has two end, and A and B. So there are two moment value at member AB, which is called as member and moment. Okay, for member BC, again clockwise. This is based on the sign convention. Okay, we have to first assume all clockwise. Okay, moment that act on member are clockwise, but moment at joint is opposite. Moment at joint is opposite. So beside member, we have joint. We have joint B, we have joint C, we have joint C, we have joint C, we have joint D, D is fixed, A also fixed. Okay, under the sign convention, it is mentioning that the moment that act on the member are clockwise, positive, are clockwise. That is the member and moment. However, at joint, the moment is opposite with member and moment. So at joint A, this is joint A, at A, joint moment is opposite. Okay, at joint B, we will have opposite. Okay, this is also opposite. Okay, this is also opposite. Okay. Member and moment and join moment. Member and moment and join moment has opposite characteristic. Member and moment and join moment has opposite characteristic. If the member and moment is positive, the join moment is negative. If the member and moment is negative, the join moment is positive. Okay? The member and moment and join moment has opposite characteristic. Okay? Member and moment and join moment has opposite characteristic. Okay, member and moment and join moment has opposite characteristic. Member and moment and join moment has opposite characteristic. And this is very, very important to understand, because whenever we want to distribute moment under distribution row, we have to change the direction because of this characteristic. Because at level distribution, the upper value is member and moment. The upper value, in order to distribute moment, we have to change sign. Okay, the change sign means opposite characteristic, because we distribute joint moment. If joint moment is given directly, like the previous example just now, okay, if there is an external moment that is subjected directly at join, that is already join moment, so we have to times the factor directly. But if the join moment we calculate from previous the upper value, previous step, okay, from the upper value, from the value from the member and moment value, so we have to change sign. Because fixed and moment, for example, is member and moment, we have to change to join moment, and after that we have to distribute join moment. So that is why there is a step under the distribution where we need to change sign, and I believe you have done this previously during diploma time. Okay, we have to change sign whenever we distribute moment, because of the opposite characteristic of member and moment and join moment. Okay. Okay, the first step that we need to do before we draw the table and do distribution moment. Okay, of course we have to calculate k. So there are three members, so there are three value of k. Okay, there are three members. We have member AB, so we will calculate KAB, KBC and KCD. Three value. KAB, KBC, KCD, because of three element. KAB, KBC, KCD. Okay. Uh, if you do not want to get confused, actually you can also call this as BA as well. So this is also the value for KBA. KBA and KAB is the same. Don't get confused. Okay, so KCB, so KBC is the same. KCD, KDC is the same. KDC is the same. Okay, so for AB and DC here, because AB refers to NA, DC refers to ND, the value is 0 because of the support. It refers to fixed support. It refers to fixed N. Okay, it refers to fixed N. However, all internal, okay, we have to calculate the value. We have to calculate the value. So there will be DF. Okay, how, don't remember all this BA, BC, CB, CD, all this, because we have to get from this. Okay, we have to get from this. So for member AB, we will have, this is MAB. Okay, MAB and MBA. The moment at NA for member AB is MAB. The moment at NB for member AB is MBA. Okay, so for member BC, we will have MBC and MCB. And the moment for member CD is MCD and MDC. So there are 6. So there are 6 member and moment. So we should also have 6 distribution factor. 6 distribution factor. So from this, we should know that we will have DF, AB, DFBA, DFBC, DFCB, DFCD, and DFDC. So there are 6. So that is why there are 6 value shown here. Okay, DFBA, DFBC, DFCB, DFCD. Okay, DFAB and DFDC. Okay, so that is for distribution factor. And then we continue to calculate fixed end moment. Fixed end moment, since member BC and member CD, member BC has UDL, member CD has point load, and due to the behavior, the FEM, we will get 1 negative, 1 positive. That is why we get this 1 negative, 1 positive. So same goes to CD, we get 1 negative, 1 positive. 1 negative, 1 positive. And after that, we will start. Okay, we will start after this. The moment at joint B and C are distributed simultaneously. These moments are then carried over simultaneously to the respective end of the span. The resulting moment are again simultaneously distributed and carried over line 7, 8. So all this representing the process in the table. Okay. This is actually the process in the table. Okay, so the table should have the table should have. Okay, we have to list all the members. So 3 members, 6N. So we have ABBA, BCCB, and CDDC. Okay, and there are 4 joint. We have joint A, joint B, joint C, joint D. Okay, joint A, joint B, joint C, joint D. And after that, each members, we have distribution factor. Okay, DF, AB, and DFDC 0 because both end are fixed. And DF at B, DF at C, total must get 1. DFBA plus BC, 1. CB plus CD also 1. Okay, and then the first member and moment in the table is FEM. One negative, one positive because of the behavior. So that is why we get this as negative 240, positive 240 for member BC, and for member CD we get negative 250 and 250 for member CD. Okay. So after that is the first distribution in the table. Okay, remember, I repeat again and again, under distribution we have to distribute joint moment. We have to distribute joint moment, and the value, the upper value means this value, this value, this value. Okay, for for B, the joint moment is this, means 0 and negative 240. Change to joint moment, it will become positive 240. Change to joint moment. Okay, because previously I have explained about the opposite characteristic of joint moment and member end moment. So the moment that we distribute is joint moment. So for B, the joint moment is positive 240. Positive 240. That is why the positive 240 times 0.5, we get 120 positive. We get 120 positive. So actually, we can check whether it is correct or not. Okay. So this 4 value, the total must be 0. Total. Okay. Same as the previous diagram shown. Okay. About the 2000 moment applied at joint. And then we distribute moment to AB, AC, AD. And total, we will get back 0 to remain equilibrium. Okay. So move to C, joint C. Joint C, for joint C, this is joint C. Okay. Joint C, we have, okay, moment from CB, which is positive, 240. And we get another one from CD, which is negative, 250. But this is not the joint moment. So joint moment means this 240 and this 250. This is joint moment. Okay, this is joint moment. So total this is negative 240 plus 250 is 10. So the joint moment is 10. The joint moment is 10. That is why when times with 0.4 and times with 0.6, we get 4 and 6 positive. And another checking that can be made is this 4 value must equal to 0. Okay? Equal to 0. Okay. Actually, the 250 at DC also we have to distribute, but the factor is 0. And the moment value in the table, when equal to 0, we do not write the 0 value in the table. So leave as blank like this. Okay? Okay, that is the distribution in the table. Distribution in the table. Okay, next step is we have to do balancing. We have to do balancing. We have to carry over the value. We have to carry over the value. Okay, we have to carry over the value. Okay, by using the factor. By using the factor. Okay, the factor is 0.5 for N fixed and internal support. For N fixed and internal support. So based on this one, all will be used 0.5 based on this. So for AB and AB is fixed 0.5. BA internal 0.5. This is the factor. BC internal 0.5. CD internal 0.5. CD also 0.5. DC and D is also 0.5. So what happened is we have to carry over, we have to do balancing using the factor 0.5, and the value we must put like this, carry over. The 120 we have to carry over, 120 for BA we have to carry to AB. It must cross boundary. We bring the value from B to A and B to C. So B, we have to B, belah sini ada A, belah sini ada C. So we have BA and we have to bring to BA, we have to bring to BA, we have to bring to AB, and BC we have to bring to CB. Okay, by using the factor. So the value we times with the factor. And at this level, we do not need to change sign. Okay, we don't change sign. Change sign means we distribute moment, not balancing. Change sign, we distribute moment, not balancing. Okay, under carryover or balancing, we have to carry the value to opposite join. Means B, we have to carry to A. B also we have to carry to C. Okay, so at CB we have to carry to BC, and CD we have to carry to DC. Anyway, actually the process is like this, but zero value we don't put. Okay, that is why we get just like this. Okay, this is cycle number 1. Okay, finish one cycle. Then after that, we have to repeat the cycle, repeat the process. Carry over, then distribution again. Then carry over again, then distribute again. Carry over again, distribute again. Okay, we have to do the process until the last distribution reaches 0.0. Okay, reaches 0.0. So when you find 0.0 under the last distribution, means that you may stop the process. You may stop the process. Repeat the process again and again and again. Okay, normally 5 times, sometimes 6 times. Okay, 6 time distribution. Stop at distribution, and finally we have to total all the moment in the table. We have to total the moment in the table. Total the moment in the table. Okay, so we have to stop at distribution, and after that we have to total all the moment. Start from the first moment in the table. The first moment in the table, is FEM. Okay, then all this is the member and moment, the internal moment. So this is internal moment. Internal moment. Internal moment. Okay, this is AB, MAB. This is MBA. This is MBC, MCB, MCD, MDC. Okay, and don't forget this one, these two value. Okay, we will get opposite in order to get because B is roller. So when we combine back, the moment should be 0. Okay, that is why at B and C we will get 0, the total. So this one is MB, and MB is MBA plus MBC, and this is equal to 0. That is why the value 1 negative, 1 positive. Okay, same goes to CBCD. Same goes to CBCD. CBCD also the same. Okay, so for MC, we have MCB and MCD, and this is equal to 0. This is equal to 0. CB plus CD, one negative, one positive. We will get one negative, one positive because we will get back the roller. Okay, the moment because the moment at roller is 0. So when we combine back, so we will get back the 0 moment at roller. Okay, so MC is equal to 0, MB is equal to 0. The internal, when we combine, we get back 0, unless the external moment is given at that joint. Then we will get the moment value. Okay, so MAB and MDC, we have value because it is fixed support. Fixed support has moment value. Fixed support has moment value. That is why AB and DC has value. Okay, so the internal moment from the table, actually we can continue this to draw the bending moment diagram, because bending moment diagram is very very important thing that you have to understand. Okay, and using this moment value and and considering moment direction, actually we can draw, or we can sketch the bending moment diagram. Okay, let's do it now. Okay, we have AB, BA, BC, CB, CD, DC. Okay, look at the value. Look at the value. Okay, by considering the moment sign. By considering the moment sign, AB has positive moment, BA positive, next negative positive, next negative positive. The moment direction. Okay, so AB positive, AB positive. So AB ni, it is positive. Okay, BC, BC is BC is negative positive. BC is negative positive. CD is also negative positive. Negative positive. Okay, this is the moment direction that we get from the end moment in the table, the end moment, the internal moment in the table. Okay, so from this, actually we can sketch the bending moment diagram. The bending moment diagram, don't forget, member BC has UDL here and point load. Okay, so this will guide us how to draw the bending moment diagram. Okay, for AB, the diagram is like this. So this arrow means the point is here. This arrow means the point is here, and this is the last point. Okay, so we just need to join this line. So this is the BMD. This is the BMD. This is positive and negative. Okay, so next one. Next one we have, okay, the first and the last position should be 0. The first and the last position. Okay, this means somewhere here. This means somewhere here. Okay, and because of the UDL, so we should have the curve line. The curve line where the maximum moment, we can get from the shear force diagram. The maximum moment we can get from the shear force diagram. And for the last one, okay, for the diagram, this is the first position, this is the last position. First position and last position. And then based on the arrow, this is the point. Based on the arrow, this is the point. And due to this point load, we get one maximum moment. Okay, one maximum moment here. But point load, we have the straight line. The straight line. Okay. So we just need to put the value. So this is 234.3. We get 281.5. 281.5. 125.2. And 62.5. Okay, the sign. Okay, this is positive, 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 negative, negative, negative. Okay, so don't worry if you find that why this is negative, and in the table it is positive. In the table it is positive. So why it is negative in the diagram? Okay, why it is negative in the diagram? This is positive, but in the diagram, okay, it is negative. That is because okay, that is because this negative plus the positive in the table, plus the positive in the table, means that the last position, means that this negative 125 plus 125, we get back to 0. This is the end point. So all end point, when we draw in opposite. Okay, same goes to this. This is negative 281.5. Negative 281.5. But in the diagram, it is positive. Positive because this negative 281 is not the end point. The end point is 0. The end point is 0. This is the end point. Endpoint. So means that this negative 281.5, we plus with positive 281.5, we get back to endpoint, 0 position. Okay. So this is actually the bending moment diagram that we can sketch from the moment value that we get from the table. Okay, careful with the loading on top of the member. UDL, we may have this shape, the curve shape, and for the point load we have the straight line, but it still have maximum moment. And for the value for the maximum moment for member BC and CD, we have to calculate from the shear force diagram, because the area of shear force diagram representing the moment value. Area of shear force diagram representing moment value. Okay, so Of course, we have to do some calculation applying back the static equilibrium. It is just like we analyzing simply supported beam. So we can we have to calculate the shear value or the reaction at each end, and then we draw the shear force diagram. And after that, from the shear force diagram, we can identify the maximum moment. Okay, so sometimes there is no maximum moment. Sometimes it has maximum moment. It will have maximum moment whenever there is an intersection in the bending moment in the shear force diagram. Okay, when the shear force diagram is like this is shear force diagram. It means that it has maximum moment. But if shear force diagram is if shear force diagram, for example, if shear force diagram is trapezium, if shear force diagram is like this is social shear force diagram. So this mean the maximum moment point. So maximum moment occur, okay, at intersection. Intersection. Trapezium means no maximum moment in BMD. This is shear force diagram. This is shear force diagram, but trapezium means no maximum moment in BMD. Intersection in shear force diagram means there is maximum moment. Okay, so where is the maximum moment? At the intersection. At the intersection. So we can only get the maximum moment value in the bending moment diagram when we analyze the shear force diagram. Okay, so you can check back the answer okay, given here. Okay, actually in this example, the shear value is also calculated. The shear value is also calculated. So the shear value here, okay, should be calculated using the static equilibrium. So using the shear value, we draw the shear force diagram, and that is why in this case we get, okay, we can see that the maximum moment has value. Okay, so I think that's all for this session. Inshallah, we will continue. Okay, doing one more example. Tomorrow night, inshallah. But about 10:30 p.m. night. Okay. So thank you very much. Thank you very much. Thank you for joining. So hope you understand. If you don't understand, please ask any question. Okay. Thank you very much. We end the session with Assalamualaikum warahmatullahi wabarakatuh. Good night, everyone.